Morning here. Right. Hi, everybody. Good morning. It's my great pleasure to introduce Professor Mingrui Liu from University of George Mason. Mingrui is currently assistant professor in computer science department. And his research interest is on foundational AI, including machine learning, numerical optimization, machine learning theory. And his research has been recognized by the recent III new faculty highlights, right?
Last year.
Last year, okay, okay. And today, I think Mingrui is going to talk about something very interesting. It's about the interplay of optimization and the neural network training. You probably will hear something very striking to you today. Okay, Mingrui, go ahead.
Okay, thank you, Ju, for the nice introduction. Can everyone hear me?
Okay, yes.
Anyone from Zoom can hear me? I want to make sure,
So maybe you can hear this because
okay.
they are doing
Other recording?
Yes, be better to just test here.
Oh, good.
Yeah. And you want to put in your pocket?
Oh, sure. Somewhere. I never use that because my sound is large enough. Okay, no problem. Thank you. Yeah. Okay. Good. Yeah. I'm very happy to visit University of Minnesota. First time to come here. Yeah. Today I'll talk about beyond black box analysis, understanding the role of local updates in distributed learning. So this is joint work with my students, Michael Crawshaw, and my visiting student, Yajie Bao from Shanghai Jiao Tong University. Blake Woodward is a faculty at George Washington University, and Amar Shehu from George Mason University. And we have observed empirical success of deep learning. We don't need to motivate that too much because deep learning is so successful these days. And deep learning is nothing but a multi-layer neural network. So we have a bunch of inputs, and we just feed those inputs into several layers, and then we get the output. Output just give you the good representation of the data, and then you can do downstream tasks, either classification or regression or next word generation, and so on and so forth. It's very cool. And people can use that for different applications. For example, in computer vision, people use convolutional neural network to learn the features and do the prediction. And also in NLP, people can use recurrent neural network or transformers to do machine translation. And also people use the generative modeling, either generative adversarial networks or diffusion models to generate new images based on the learned representation. And also in the game, people use reinforcement learning or policy neural network to play the game. Okay, deep learning is very successful. And what's the underlying math of deep learning? That's the central topic of today's talk. Okay, so deep learning is basically, what is deep learning? I want to do the mathematical side of deep learning. Okay, so deep learning is nothing but this kind of neural network, and this neural network is related to AlexNet, which is actually the first neural network who basically works in the large scale. This one won the ImageNet competition in 2012. Okay, and what the AlexNet looks like, and the input is X, and W is the model parameter. It can be the parameters of different layers. And we pass through the X to different layers. For example, W1 is the first layer. Sigma can be activation function, value activation, for example, W2, and so on and so forth. This convoluted function. And training a deep neural network is nothing but minimizing a loss function like this. And here the L is the loss function, FWX is the the predicted output, and Y is the ground truth output. And we are trying to take the expectation and take the minimum of this function. Okay. This optimization turns out is very difficult. The reason is that the landscape is very complex. So in practice, we encounter this kind of so-called non-convex optimization or non-convex landscape. So for example, this landscape has multiple global minima, local maximum, and we have only possibly one or few global minima. And if you train a deep neural network, for example, using your favorite optimizer, either SGD or Adam or SGD with momentum, whatever, and you cannot guarantee, they can converge to the global minima because it's non-convex. For example, if you start from some bad initialization, you may converge to some, bad local minima. So that is the, non-convexity which caused the problem, which caused the difficulty of the problem. Okay. And how people train that in machine learning? People just use stochastic gradient descent. It's a very simple algorithm. I believe everyone uses that. What is stochastic gradient descent? Mathematically, it's very simple. We just want to minimize a loss function L of W. And every time we sample a data point, xt comma yt, xt is the feature, yt is the label, for example. And then we update the model parameter W by the stochastic gradient descent. And this one, the blue part is so-called a stochastic gradient. I will just calculate stochastic gradient with some learning rate eta t, and we update the parameter. Okay, and it's a very simple algorithm, but it turns out to work very well. SGD is basically approximation of gradient descent is a more noisy version of gradient descent. But the theory of SGD is people can only consider the stationary point, which means that if you run SGD, if you want to find a model with small gradient, the gradient less than epsilon, and it typically requires 1 epsilon 4 iterations to guarantee that. It's a very classical result by Gardiner and Line around 10 years ago, 12 years ago, basically. Okay, so this is a classical result for finding a stationary point. That's the only thing we can guarantee for general non-convex function. But deep learning is something beyond that. Deep learning is not a general non-convex function; it's a special non-convex function. And how can we analyze deep learning? In a real non-convex regime. That's the central theme of today's talk. Okay, good. And another regime which we are interested in is so-called distributed or federated learning. Because these days, the data are distributed across multiple devices. We have multiple mobile phones, multiple GPUs, multiple nodes. They are allocated at different places. For example, data can be distributed in Minnesota, in Virginia, in Arizona. You can check the AWS center. You can find different zones, right? And it's across different nodes. So we have to train the model together using joint forces from different locations. And these models, these nodes basically try to jointly train a machine learning model like neural networks. For example, this picture means that, okay, we have a cloud. They store a global machine learning model. And we have lots of local data model. We have a lot of local data and model stored on mobile devices. And in practice, people just do the multiple local update. Let's say I train a model on my phone for 1 day. And at night, when the phone is idle and it's plugged in with some electricity, then they can upload the model parameter to the cloud. So that's the usual training regime. You cannot expect your phone to synchronize with other phones or the cloud at every time. That is at every iteration. That is impossible. We have to do multiple local updates. Let's say wait for 1 day and then synchronize the model to the cloud. So that is basically the regime people are using in today's machine learning practice. Okay. Yeah, and in short words, local updates become the important principle in distributed learning. So that's the empirical statement for today's deep learning. Okay. What is this local update? What is local SGD in distributed learning? That's the central algorithm we are going to analyze today. It's a very simple algorithm. Let's say we have 2 devices, and the device 1 basically run multiple steps of gradient descent or stochastic gradient descent. As before aggregating the weights with the client 2, device 2, which means that, okay, I just update for a few iterations and then I communicate and do the averaging with the other device. Okay, this is a very simple algorithm, but it turns out that this becomes the paradigm of training large neural network on the distributed data. Okay, and if you do the local SGD in practice, you can observe some interesting phenomena. So these are 2 empirical pictures from a cite from those 2 papers. And the first picture is basically the horizontal axis is time, and the vertical axis is basically the training accuracy. And you can see that the training accuracy always reach 100%. And different color means that they have different step of local updates. So for example, the red curve means that h equals 1, which means that they don't synchronize. They synchronize at every iteration. And when you increase h, you can see the training is faster. Right? For example, the red curve is the slowest one, and then the green curve is faster than the red curve if h equals 2. Okay, and so on and so forth. When h is larger, then the update is faster. Okay, that's the first empirical observation. There are 3 empirical observations. The first one I call it local steps accelerate convergence. Okay, that's the empirical statement. I don't prove anything about that yet. And the second statement is local SGD can achieve 100% training accuracy, right? That is an empirical statement, but it's non-trivial to prove that because, as I said, neural network is a non-convex function. And how can we guarantee we can find the perfect minimum which achieve 100% training accuracy? That's the second empirical statement. And the third one is related to this figure. Is so-called local SGD generalized better than mini-batch SGD. Okay, so this figure is the test accuracy versus the number of epochs with different h. H is the number of local updates. So if you see h equals 1, which is the naive distributed training algorithm, which is mini-batch SGD, in that case, the generalization is very bad and is oscillate, right? It's the orange curve. But if you increase h, the generalization performance is better and more stable. And what's the reason for that? So these three empirical observations cannot be explained by any theoretical results. So, in short words, the benefits of local updates cannot be interpreted by the standard theory in distributed optimization and learning. And in today's talk, I'll try to solve this problem by doing another type of theory to solve those problems. Any questions before I move on?
So if you have these kind of benefits, how would you implement this in practice?
Implement what?
Implement the local updates. You just, I mean, let's say you have a data set and you can fit on one single GPU. So it's an implication that I would purposefully divide the data set into multiple local size.
You can do whatever.
Emulate multiple local size.
That's a good question. So basically, it depends on your setting. If you are doing federated learning, the data is inherently from local devices. You cannot divide data. And the local update is useful. And if you have the HPC setting, you have the cloud setting, you have every data, you can divide them in any way you want. And what I want to argue is that local SGD is always better than mini-batch SGD empirically. And you should do local update instead of synchronization. It's basically skip communication for free, right? Because typically, if you do multiple local updates, the performance will be expected to be bad. But empirically, it's always better than mini-batch SGD.
But when you talk about a mini-batch SGD, are you talking about a centralized version?
Centralized. Exactly. Every time at every iteration, you synchronize the output of the model. Synchronize the weight of the model. Yes.
Okay.
Yeah. This is a very surprising phenomenon, and it cannot be explained by any existing theory in distributed optimization. And so that is what I'm going to focus today. Okay. Good. Any other questions? Good. Okay. Then let's move on. Before I talk about my new theory, I want to emphasize. I want to tell you a little bit about the standard theory, which I call it black box analysis. If you read those classical textbooks in optimization, either Nestrov or Nemirovsky, they would mention the black box view of optimization. The idea is that they consider a class of functions. For example, the function can be smooth function, convex function, and they develop optimal algorithm with upper bound and lower bound. For example, everyone may know the Nestrov accelerated gradient descent, which is the optimal one for the smooth convex optimization. Okay, and I also want to say something about the standard theory. For distributed optimization. Okay, the mathematical formulation of distributed optimization is the following: we want to jointly minimize this function f of w. Here, w is the model parameter. Okay. And this function is actually a summation, average of capital N individual functions. And capital N is number of clients or number of GPUs, whatever, number of devices. And Fi is defined as the expectation of this capital F function, and the Ci is the data. And Ci is sampled from Di, and Di denotes the distribution of the data. The Di can be different at different devices. Every device can have different data distribution. And then if I run local SGD with learning rate eta for capital K local steps with R communication runs. So that's the algorithm I'm going to use. Okay. And what can I say about this algorithm using standard theory? So in standard theory, people typically make some black box assumptions. Okay, I don't know what the function looks like. I just assume the function is L smooth, convex or non-convex. And also I assume the gradient similarity bound. Okay, the idea is the following. I want to measure the similarity between the data across different devices, but I don't know how to measure that, right? So people just use this assumption to measure the similarity, okay? The gradient of Fi minus gradient of F is bounded by kappa at some point, right? So it means that, okay, if the data are the same, then this kappa equals 0. If data are different, the kappa can be large, right? That's the assumption people use in theory, okay? And under these assumptions, there are some theoretical result, which is kind of inconsistent with the empirical result. I use the word quote here because I will explain later why the quote. Okay, it's not really inconsistent, but it seems to be inconsistent. There are some results. The first paper by Patel at Code 24, they show some surprising result. They show that local steps cannot accelerate convergence for heterogeneous convex quadratic functions. What's the meaning of that? We know local steps always accelerate empirically, but they can construct a simple quadratic function such that the convergence rate is something like this. It's L over R plus L kappa squared over R 2 over 3. What's the meaning of that? You can see that there's no capital K here. Capital K is the local steps I'm running, which means that even if I run for a long time, I don't accelerate the convergence. They prove this lower bound. They prove for the quadratic function is not going to work, right? Which means that we need to go beyond this analysis to reflect the deep learning practice. Okay, that's the first theoretical result, which is kind of inconsistent with practice. And also the second one, typically people unimproved local SGD can converge to stationary points for general non-convex function. It's fine because it's general non-convex function. But in practice, as I said, they will converge to the 100% training accuracy, which means that is always the global optimal solution. And what's the reason for that? It's still kind of inconsistent with the empirical result. And the third one is that if I try to prove some generalization bound for local SGD and mini-batch SGD, generalization, not optimization, just generalization on the test data, and their bound are roughly the same, you cannot see, lot of difference from the bound. Okay, but empirically, local SGD generalize better than mini-batch SGD. You can remember the curve. If they don't communicate, if they communicate at every iteration, the generalization is bad, right? So these three theoretical results means something. Means that this kind of inconsistent means that we have to get rid of the black box assumptions for analyzing what's happening in deep learning. Okay, so that is today's talk. Here, this slide is the most important slide. It's my central argument for today's talk. The first point is that we want to go beyond the black box analysis of distributed optimization and learning. And my approach is showing that for certain machine learning problems, local updates are probably beneficial. Okay, so I will use 3 examples to show that. The first example is logistic regression. It's a very simple problem. But for this problem, I can say something about local updates, okay? And note that the logistic regression can be regarded as the last layer of a neural network because typically people use neural network to do the classification or next token prediction. They always use cross entropy loss. That is nothing but logistic regression or a variant of that for multi-class, right? And also the second example is the 2-layer neural network with Gaussian input. It's a simplified setting, but I can say something concrete under this setting. Local update is very useful. And the third one is 2-layer neural network with feature heterogeneity. So that is regarding the definition of heterogeneity in distributed learning. Remember in the black box assumption, they typically use the gradient similarity as the measure. But I argue that I need to use the data feature heterogeneity instead of the gradient heterogeneity, which can show the benefit of local updates. So that's the the plan of today's talk. Any questions? If I move on. Okay, good. Yeah, and then I'll go to the first part, which is the paper I published at iClear this year. And the main, claim of this paper is that I can prove local updates probably accelerate local gradient descent for logistic regression. Okay, and I'll tell you some details here. First, I want to define the problem setting of heterogeneous logistic regression. It's a very toy machine learning problem, but people don't even understand this problem very well. Okay, and the problem setting is the following. We have capital N machines, and each machine, the mth machine, have some data samples. We have XMI, YMI. XMI is the feature, YMI is the label. And we have small n number of data, okay? And suppose data is linearly separable, which means that I can find the linear classifier, which can classify every point correctly. And also we want to minimize this function. This formulation is the same as before. We just categorize the FMX of W, which is the logistic loss, right? Average over the logistic loss. Okay. And if I run the local gradient descent with learning rate eta with for k local steps and R communication rounds. If I use the black box analysis, what can I get? Okay, here I will show the analysis of this algorithm by state-of-the-art black box analysis. Okay, it's not my paper, it's other people's paper which achieved the best bound. Okay, the first paper is by Woodworth et al. They need to choose the learning rate to be 1 over k R to 1/3, right? In that case, they can show the F W hat. W hat is the output of the model after k local step and R communication rounds. You can get this bound. Okay. And then another paper which shows a slightly different bound. If they choose learning rate to be 1 over k, they can get this bound. Okay. So what's wrong with these two bounds? Okay, the key thing is the following. The dominating term of this bound does not decrease with k. That's the problem. Okay, if you check the first bound, 1 over kr plus 1 over r 2/3, the second term is dominating. This one has nothing to do with k, right? Which means that I run many steps of local updates, it does not accelerate, does not help. That's the first problem. And also the second one, you get 1 over r here, which means that the k is not useful at all, right? So that means that the black box analysis cannot explain the local updates help optimization. But for this problem, we can prove another algorithm, which is a variant of local gradient descent, can indeed accelerate optimization. Okay, that is from the second slide. Okay, if we use the, let me go back to the previous, let me tell you what's the problem of the previous analysis, why they cannot have k dependency here. The real reason is that they have to choose the learning rate eta to be 1 over k. That's the, if you use black box assumption, you have to use this kind of step size, because if they want to choose the step size to be small such that the client drift, which means that they have to do local updates for many times, they want to compensate kind of client drift by decreasing learning rate. That's the real problem they are facing in their analysis. Okay, and how can we solve this problem? We use the two-stage local gradient descent. So the key observation is this property, which is crucial for logistic regression. What's the property we are using? For logistic regression problem, when the loss is small, the smoothness constant also becomes small. Okay, this property is very crucial. It does not hold for quadratic function. Okay, for quadratic function, the smoothness constant is always a constant. Let's say quadratic function is L, is always L at any points. But for logistic loss, the smoothness constant will change according, during your optimization. If you are close to the optimal solution, your smoothness constant becomes small. That's the key observation we are leveraging in the proof. Okay. And then how can we design the algorithm based on this observation? We can use two-stage gradient descent. In the first stage, we can start from a small learning rate and then switch to a large learning rate later. And if we switch to a larger learning rate, we can get acceleration. That's the idea. And I have a pictorial illustration for this idea. Okay. The algorithm, this is basically the trajectory of logistic regression. And you have two stages. In the first stage, we still need the learning rate to be less than 1 over k, because otherwise, otherwise the smoothness constant is too large, and you cannot use very large learning rate to do that. And after that, after this transition time, I define the transition time as the following: the smoothness constant less than the loss, less than 1 over eta 1 times k. Okay, this one means that when my loss is small enough, the smoothness constant is small enough. In that case, I can use larger learning rate. So the stage 2, I use eta 2 is much larger than 1 over k. In that case, I can have acceleration. So that's the idea of two-stage local gradient descent. Okay. Any questions? Okay, good. And here is the theoretical result for local step accelerate local gradient descent. If we run local gradient descent for heterogeneous logistic regression with 2 stages, in the first stage, we use this learning rate 1 over k for all tilde k steps. And for stage 2, we run constant learning rate with the rest of the steps. Okay, and we can get this kind of guarantees. The output solution is big O 1 over k r minus r0. R0 is the first stage iterations. Okay, what's the implication of this theorem? The first implication is that for large enough R, local gradient descent for logistic loss has convergence rate order 1 over kr. Okay, because here is r minus r0, R0 have order k. As long as R is large enough, we can basically ignore this R0 stage. Okay, so we can get 1 over KR convergence rate. And this convergence rate is much better than the previous one because I have explicit K dependency in the convergence rate. If I run more local steps, I have faster convergence. And all the existing guarantees for local SGD applied to any problem previously are at least omega 1 over R, right? They do not show the benefit of K. We show that. Okay, that's the difference here. And the key idea is to use large step size at the very beginning, at the second stage. But previous analysis requires eta to be less than 1 over K. If you read previous papers, Woodward's and Klaus-Koba, those papers, they typically rely on this assumption for their proof in the black box analysis. And this is the theoretical result. Okay. And we have verified our theoretical result by some simple experiments. We did 2 experiments, which is synthetic experiments and heterogeneous M-NIST experiments. And if you use this kind of small step size, by the way, H is the smoothest constant here, and K is number of local steps. If you use the previous theory, you have to choose the learning rate to be 1 over KH, right? And even use different K, the learning curve, they overlap, which means that even if you use large K is not going to help. But if you use our 2-stage type of learning rate, eta 1 is 1 over KH, and eta 2 is 1 over H, you can see that if you increase number of local steps, the convergence is much faster, right? If K equals 1024, this curve is like this. It's much faster than the previous one. Okay. That's the first part of the today's talk. Any questions? Yes.
Is there any specific turning point where you switch to your second stage?
Yeah, good question. So I need if you check the picture, it's easier to understand. When my loss is less than 1 over eta K, I switch to second stage. And I know if I run K steps, I can prove the loss will be less than 1 over eta K. So that's why in my theorem, I have the R0, which is O tilde K. The tilde means that I ignore some log factors. If I run O tilde K steps, I can guarantee the loss is small. And after that, I can run large learning rate. Yes.
Thank you.
Good. Thank you. Any other questions? Good. Then let's move on to the second part. The second part is the global optimization analysis of local SGD with neural networks. So the motivation of the second paper is the following. So as I illustrated at the very beginning of today's talk, for non-convex functions such as the neural networks, local SGD can empirically converge to a solution with 100% training accuracy, right? That is by the Makamahan, the very first paper of local SGD. They showed that empirically. But if you want to show that theoretically, you have to show the global convergence, which means that you have a non-convex function. You start from some initialization, you run gradient descent or the local gradient descent. You want to converge to global minimum, right? There are some related work which try to show that. The first work is trying to show, they can only show proof of stationary point for non-convex function. And also there are some papers which try to leverage problem structures to show the global convergence. So they basically assume the neural network is over-parameterized to enter the kernel regime. The kernel regime means the neural tangent kernel. If you work on the deep learning theory, you may know that. It basically means that it's nothing but the kernel linear regression problem over feature mappings. The feature mapping is defined by the kernel. Okay, and there are some work which trying to show the local SGD is basically the kernel regime, and you are doing linear regression over kernel feature mappings, and so it's easy. It's a convex problem. But we are not interested in the kernel regime because kernel regime cannot learn features. So we want to go beyond feature kernel regime. So the question we are trying to answer is that can we formally prove the global convergence of local SGD beyond kernel regime? Which means that we don't have a lot of parameters. We don't have over parameterization. How can we prove the local SGD can converge to global minimum? Okay. So here's the problem setting. We consider a specific 2-layer neural network in a distributed environment. Okay. Here the Z is the data, and V is the first layer, and A is the second layer. You can see that the second layer have the weights K, and the Z is basically the training data, and V is the first layer. Okay, we use layer normalization here for the first layer. Okay, and we assume the data Z is Gaussian. That is very important because if you don't assume any distribution, there are some hardness results showing that the function is very difficult. The problem is NP hard, and so on and so forth. And in the real world, we can assume some data assumption. The Gaussian is just for simplified analysis. Okay. And for the Gaussian data, we have a teacher network, which is C W star A star. W star A star is basically the ground truth parameter for the first layer and second layer. So the learning process is the following. We want to learn a student network by collaboratively minimizing the mean square loss over capital N local clients. So we are trying to average this kind of square loss. Okay. And Y is the ground truth teacher network output. And here the FZVA is basically the student network. They use the exact same parameters, and we want to minimize this loss function. Okay. And if we use that example, there are some nice geometric property of the loss landscape. The good thing of this loss is that this loss function have one global minima and one local minima. You can see that this minima is the local minima, and this minima is the global minima. We only have one superior local minima, right? It's a real non-convex function. It's nothing close to linear regression. It's a real non-convex function. Okay, and how can the local SGD algorithm get rid of the first superior local minima and enter this global minima region? So that is something we are going to prove today. Okay. So there are some related work on this problem structure. The most two important related work about these two papers. The first paper by Du et al. They show that if you initialize first layer weights and second layer weight randomly in some ball, then if the initialization are from the attraction basin, here is the definition of attraction basin, which means that the first layer and the ground truth, the angle are actually accurate. And also the second layer and the ground truth initialization is also accurate, which means that is in a very nice region. It's basically in this region. If you initialize in this region, the function is locally convex, then you can converge to the global minima. Okay? But you cannot really guarantee that if you randomly initialize V and A uniformly randomly, you can enter this. You can enter that attraction basin. That's why the paper only had constant probability to converge, which means that if you are lucky, you enter this good region, you can converge. Otherwise, you cannot converge. Okay, that's first paper by Du et al. We solve this problem. Use constant probability convergence. And there's another paper which is using the perturbed gradient descent. Right. The idea is that they want to inject some noise carefully at every step. Okay. The idea is that when the landscape is very, have some superior local minima, you have some global minima, you can introduce some noise to smooth out this superior local minima. In that case, after perturbation, the landscape becomes benign, and then you can converge to global minima. Okay. But this algorithm is not the algorithm people use in practice. It's a very carefully designed algorithm which want to introduce noise with the right magnitude. So that is very fragile. If you change the architecture, if you change anything, this one may not work at all. Okay, so that's these two papers' theoretical results. And how our work is different than these two papers. We first we want to introduce local SGD algorithm, which is simple because we already discussed that. We update A with local gradient descent. We update V with first layer with local gradient descent. Okay, that is simple. And we first did some experiments to show something interesting. So we start, we just choose any initialization. I choose any initialization, even if it's in the bad region. I run this algorithm of SGD. It's just SGD, not even local SGD. It's a simpler version of SGD. I can show that, okay, the cosine, the phi t means that the angle between the first layer with the ground truth. And AT transpose A means the second layer at T's iteration transpose with the ground truth A star. And you can see that the cosine phi t can converge to 1 finally. Even if the cosine phi is negative at the very beginning, it will become positive and be converged to 1 finally, which means that they will align with the teacher network, even if the initialization is very bad. At the very beginning, it's the opposite direction, not opposite, basically the obtuse angle with the teacher network. But after the SGD algorithm, it can converge to the ground truth. And same thing happens for A. And A can align with the ground truth as well because the inner product goes to 1, right? And also the loss goes to 0. Okay. So this means that even if I initialize at the bad region, the algorithm is smart enough to perform some self-correction, which can correct the initial wrong signal during the training process by itself. So that is the terminology. I call it the terminology so-called self-correction. Okay, which means that the algorithm can correct the wrong signal by itself, even if I'm not lucky enough in the bad iteration. That's the empirical statement. And how can we prove that? So here's the proof roadmap. The main contribution is that we found the self-correction mechanism in the vanilla SGD or local SGD. The algorithm is smart enough to correct the wrong signal, even if I'm not lucky enough from initialization. And second one, we don't require over-parameterization, which means that we don't enter the kernel region. We are really doing non-convex problems. And third one is that we can show linear speedup of global convergence. That is the desired property of the distributed learning. And here is the idea of the proof. I have a picture proof, nice picture proof later, but here is some notation I want to introduce you. The phi t is basically the angle between the Vt and W star. I introduced the phi t before. And we want the phi t to be close to 0, right? And for the arbitrary initialization V0 of A0, except for measure set phi 0 equals pi. This one is just try to exclude the situation that you are exactly at the superior local minima. At that point, the gradient is 0. There's no way to escape. But except for that point, I can always escape. So I can say, I can always escape using the local SGD algorithm. And the proof is actually the proof is actually in the 3 stages. The first stage, I want to show the AT transport A star can turn to positive in polynomial time, even the initialization is negative. That is so-called self-correction of the second layer. Even if the initialization is negative, it can turn to positive. And second, I can show that the AT transport A star can keep positive, which means that the second layer is already correct. And then the first layer will decrease below pi over 2 in polynomial time. So which means that the second layer is already correct, and then I can correct the first layer in polynomial time. And then after step 1 and 2, I enter a nice attraction basin, which is a locally convex region. In that case, I can converge to the minimum with a linear speedup guarantee. So that's the proof roadmap. And I have a nice picture proof in the next slide. Maybe it's more intuitive. So I have 2 axes. The horizontal axis is cosine phi t. We want cosine phi t to be 1 because the phi t in this case is 0, will be 0 if you converge to 1, right? And the second one is AT transpose A star. And I want this one to be close to 1 as well. So this point is the final point I want to reach, right? And at the very beginning, I may not be very lucky. I may initialize at some bad region, A0, V0. In that case, both these 2 quantities are both negative, right? And it's very difficult to optimize because you are in a you are in a very difficult region to optimize. And then the red part is showing the self-correction of the second layer. Because the signal of A will become positive. It's initially negative, but it will become positive in tau A steps. Tau A is a very small constant. And then this curve is showing the self-correction of first layer, which means that after the second layer is corrected, I can correct the first layer. And then when I reach these points, this region is easy region, which is the attraction basin region. It's locally convex, so I can converge quickly to the global minimum. So that's the pictorial proof for the paper. Any questions? Yes.
So I'm trying to think about the intuition behind, why this is helpful. So when after your multiple local updates, how do you do the aggregation? Are you just taking the average?
Taking the average, yes.
Okay.
Mm-hmm.
Because this reminds me of a technique called technique in global optimization. It's called a particle swarm. Or the family of ideas. The family idea is basically, okay, so I do multiple simultaneous optimization of the same landscape. And then, every once in a while, I try to average the interest. And this kind of averaging, tends to get me around, some bad local minima. And so, we get a better chance of getting a global solution. So I wonder whether it's the same reason here, because this does look very similar to that. because every of your local stochastic gradient is working on one version of the landscape.
Yes,
right?
yes,
And they are for the original landscape, they are in a different position of the space. And then every once in a while, you try to do an aggregation. That's very, very similar to that kind of idea in global optimization.
yeah. But I
So
know.
I wonder whether you have thought about this.
Yeah. So I think this is a little bit different than what you said, because even this problem I can prove SGD can converge. I don't need to do local SGD at all. Even local SGD can converge. Local SGD just accelerate convergence.
Oh, I see.
Yeah.
See.
So maybe I didn't mention that clearly in the previous slide. So there's no work showing the global convergence of SGD with arbitrary initialization, not to mention local SGD.
I see.
So I first want to prove local SGD, and then we'll show local SGD will accelerate SGD. So that's a different, maybe a different reason for that.
I see.
Yeah.
Okay.
But next question. I will read the paper you mentioned. But I think there are many papers. I think what you are mentioning is close to so-called model ensembling. So you basically
Right.
train the model with different initialization, and you get different model, and you ensemble the model.
Yeah,
That will be helpful.
because in general, they improve global optimization. That's a
Yes.
very, very common heuristic
Right.
in global optimization.
Yeah, there are some proof for that.
Yeah.
Not me, but some people prove that. Yeah, next question. Okay, any other questions? Yes?
So I'm trying to grasp this, like, if you're, that theory of, when you're looking for the minima.
Yeah.
You got kind of like the hill in the way. When you inject that noise, is that kind of similar to like you're kind of jumping up so you can kind of see the global?
Something like that. Yeah. That's the intuition. So that's why let me show you something. I mentioned that for arbitrary initialization, except for measure 0 set phi 0 equals pi, which means that if you are really bad, you have really bad luck, you are initialized at the bad local minima, there's no way to look around, so you will get stuck. But if you are a little bit away from the bad local minima, you have the chance to look at different places, and then you will converge to the right minima. Yeah, thank you. Any other questions? Okay, good. So let me see the time. I may need to move faster. I'll skip the proof. It's very technical, but I think the picture says everything. And experimentally also, I tried different initialization. The scenario A, the first column is that I initialize at the bad region, right? Is A0 equals negative A and phi 0 larger than pi over 2. I can converge to the ground truth anyway. And the second one is a little bit less bad, right? Is basically the phi 0 is right, phi 0 is good, but A0 is bad. And the C is the lucky setting. We are in the right region. We are in the attraction basin, and we can always converge. So the message is that whatever initialization I use, I can always converge to global minima for this problem. Okay, good. And then I will briefly talk about my third work about the generalization analysis of local SGD for heterogeneous data with neural networks. And this is different than optimization, but it's related. I want to show why local updates can generalize better. Not only optimization, it can generalize better. So the setting is the same. We have this kind of average loss, that's the same. And the Woodward et al., they show that local SGD is dominated by medial SGD for heterogeneous data distribution. They show that it's a theoretical result. They show that theoretical is dominating, okay? But in practice, local SGD is much better. And which means that we need to go beyond this black box analysis. That's the main theme of today's talk, right? So how can we get rid of that? What's the gap between theory and practice? Here's the gap. The gap is the definition of the data heterogeneity in the black box region. Remember, typically people just don't know how to define the data is different. They just check the gradient are different or not, right? They use the supremum over W and Fi and F gradients. They try to check this one. If this one is large, then it's heterogeneous, otherwise it's not. And I want to argue that this definition is not good, okay? Because this definition depends on both model and data. Because this Fi is coming from the DI, distribution of data, and W is the model parameter, right? When we say the data is heterogeneous, it has nothing to do with the model. The model is our choice. Nobody says that the model is the right model, right? But the data is there. We cannot change the data, but we can change the model. So I want to argue that the data heterogeneity should only depend on data itself, but not this model. Okay? And then I will show that local HGD can learn features better than the mini HGD. The feature means that you can understand some coordinate of the data, some feature of the data better than the mini HGD. And I make this claim because I did some experiments. So I do the weight visualization of local HGD and parallel HGD. And it's a little bit vague, but you can see that the left picture learns more patterns compared with the right-hand side picture. The right-hand side picture, the feature mapping is kind of blurred, but left-hand side, the picture has more distinct features. That's a very subjective, statement, but this is visually, visually more distinctive than these parallel HGD features. And I will formalize that in the theory. And how can we formalize questions? No? Okay, good. How can I formalize this insight in theory? The first question is that how to define the features of data, right? That's a big question. How can we define the feature of data? So there's a nice paper by Allen, Drew, and Lee. They have the so-called multi-view data hypothesis. This paper, by the way, won the best paper award at iClear. So I read this paper very carefully. So what's the idea of the multi-view data hypothesis? So let's say you have different pictures. You have a car, you have a cat, right? How can you distinguish whether it's a car or a cat? You check their features, right? For example, the car may have a window, have a headlight, have a wheel, right? If you see any of them, you will classify that as a car, right? Because the cat does not have window, right? You have headlight, you will classify that as a car, okay? So that is so-called a feature. The feature of a car can be a headlight, can be a wheel, can be a window. If you learn one of the features, any one of them, if you learning one feature is sufficient to correctly classify the object, right? You object capture one of them is good enough, right? Even for these two, I think a neural network can still capture is a car, even if there is no headlight feature because you take the picture in a different view, right? And this one does not have the wheel feature because of different view. You take the picture from different view, but they have some feature. As long as you can learn one feature, you can correctly classify this object. And also similar thing happens for the cat eye, right? This cat eye, if you can see the cat eye, you can classify that one as a cat, right? So that's the feature of a cat. And there is something more interesting, which is so-called feature noise. So it's very possible that for the car, when you misclassify that, you may take a look at this feature. This blue feature looks like a cat eye. If your neural network learn this feature, it will misclassify this car. That's the reason why you misclassify data. So you have feature noise. Feature means the intrinsic feature you want to learn, and feature noise means that the feature from other object. So that's the idea of the multi-view hypothesis. And inspired by this paper, we define some multi-view data in the distributed optimization. Okay, so that is another new definition of heterogeneous data distribution. We don't use the gradient data similarity. We use the feature to define the heterogeneity. Okay, so in the generalization of those papers by Allen, Drew, and Lee. And okay, here's the mathematical definition. We have a set of features, Vk star from K from 1 to capital K. We have capital K feature vectors. And we have a K0, which is the indices of confounding features with size K0, which means that some of the features are confounding features. They're not the real feature we want to learn, okay? Which is a subset of the whole feature vectors, okay? And then we define the data generation process. The DI means the distribution of i's clump. And how can we define the data from DI? We first randomly sample the label from -1 or 1, right? Is the ground truth label. And then we generate the data X based on the features, okay? The X have P features, X1 to the XP. And how can I define that? We have the feature patch. And the idea is that the first block of the X is positively correlated to the Y, right? It's like if Y equals 1 and X1 is related to VI. That's so-called a feature patch. And VI is randomly sampled from Vk star. And also we have the feature noise patch, which is something like the cat eye in a car, okay? The cat eye feature in a car. So if VI is a confounding feature, the feature noise patch I define as XP equals -Y, VP star -1 star. The key thing is the negative sign here, which means that XP is negatively correlated to Y. It's basically a feature of the opposite side of Y. So that Y is so-called a feature noise patch. And the third one is the pure noise patch. We have some pure noise, which is not related to any feature or feature noise, some pure noise, some natural Gaussian noise, for example. So that's the data generation process. And for different DI, you have different data generation process. And that is the definition of data heterogeneity, because different DI is different. Okay? And under this data distribution, we can try to understand how the algorithm learn different features using the local gradient descent algorithm. Okay? So I just let me see the time. Okay, I'll make it faster. So we consider still a two-layer neural network with cubic activation. Cubic activation is making the problem easier to analyze. It can work with NMP, but the cubic is nice enough to analyze this so-called feature learning regime. And we are doing these outputs, and this is still the logistic loss, is cross entropy loss. Okay. And this is the problem. And we consider two random initialization. The WR0 is the weight parameter, is randomly initialized from Gaussian distribution. And then we consider two algorithms. The first algorithm is gradient descent with global update, which is something close to mini-vector SGD. They average all the gradient from all the client at every iteration. And the second algorithm is gradient descent with local updates. I just use the individual data to update the model and then average that. So these two algorithms have completely different feature learning phenomena. So here is the here's the theoretical result. I use the words rather than mathematics, which makes it easier to understand. So under parameter settings, if I run gradient descent with global updates, which means that I average all the gradient at every iteration, then we have after some polynomial number of iterations, the training error can go to 0 for all clients, which means that they both can train perfectly. But the test error is very different. That's generation guarantee. The test error is almost a 0 for clients with normal features. If you learn the normal features, it's good. But the test error is 15% for client with confounding features. If you learn the feature noise, you are doing nothing no better than a random guess. You are doing the 15% error here. So that's the GD with global updates. But for the GD with local updates, things are completely different. The training error is still 0. The test error is also 0, almost close to 0 for all clients, because they learn the right features. Okay, so I'll give you the high-level idea of the proof using a picture. So the idea is the following. This is the feature distribution for different clients. Let's say the blue part, the orange, the green part is the feature. I want to learn the green parts, but there are a lot of feature noise from other classes, right? And if you average the weights, those features get averaged, so the feature signal becomes smaller, but the feature noise does not change. When you average them, it's still the same thing. In that case, the feature noise can dominate those real features if you do the averaging at every iteration. That's why, in that case, you learn the wrong signal, and you do not have good generalization. But if you do the local updates, you just learn this one and this one independently, then the green part can dominate this part, feature noise part. So that's the high-level idea of the proof. So I'll skip the real proof, but the idea is trying to categorize the signal intensity and the memorization of the noise intensity and try to compare with them for different clients. These two, actually, this is the picture proof for the real proof. I just understand the intensity of the weight correlated with different features. And if this one is large, I learn the signal. If this one is large, I learn the noise. And I want to analyze how the learning dynamics changes when using different optimization. But this is very technical. I'll skip that. Okay. And I have a few experiments. I think this experiment is more interesting. This one. Okay. So I manually add some feature noise of self-attend data set. You can see that the first row of picture is the vanilla picture. But I gradually add some feature noise here. You can see those points. They are feature noise, which are features from the data from different classes. I add some feature noise here. And you can see that if I add feature noise, the row categorizes the strength of the feature noise. If I add more feature noise, the performance is worse. But local SGD is always better than the parallel SGD because they are more robust to feature noise. So that experiment is something related to feature noise. I designed some experiment by gradually adding feature noise. Okay, good. So here's the summary. I'll just end here. So today's talk is trying to go beyond black box analysis of local SGD. I first show that local steps probably accelerate logistic regression. And the second one, I showed the two-layer neural networks with Gaussian input. I can have global convergence. And the third one is that local steps can help generalization with heterogeneous feature. I use the feature learning technique to show how local steps are helpful for generalization. Okay, and for the future work, right now I'm working on understanding the learning dynamics of more complex architectures because I'm trying previously just a two-layer neural network, which is simplified already. And right now I'm trying to understand dynamics of the modern architecture like transformer or Mamba for the structured data and what's the best communication and computation trade-off. Okay, that's the end. Thank you for your attention. I'm happy to take questions.
Hey, thank you very much. Thank you.
Yes.
Thank you for very nice talk. So for the logistic regression problem, so why your approach can work? Is there some like essential idea there?
Yeah, essential idea is here. So
well, only for like a logistic regression. What about for other problems?
oh, okay, that's a good question. Because logistic regression can be regarded as the last layer of any neural network. So that's the in the traditional optimization.
First, the part of your talk.
Oh, the first part, okay.
Yeah.
First part is here. This one.
Yes, you have this. Yeah, you do these two stages.
Yes.
So you choose a different learning rates.
Yes.
So if I have a problem, this is the composition of a strongly convex and a linear function. Can this approach
composition of strongly convex?
Because this you have logistic regression, right? It's like a log.
Yes.
And then you have some linear sort of these kind of things.
Yeah.
You have this kind of a special property. So I wonder whether that is special property plays like a crucial role here.
Yeah, it's very important. So the key property I use, here is that when the loss is small, the smoothness constant becomes small. That's the key property I use for the logistic loss. If your function have this kind of similar property, I think it's very possible to use large learning rate and get acceleration.
Okay.
Yeah. Because if you check all the papers, all the books by Nuri Nesterov, all the lower bound papers, they use quadratic functions. In that case, the smoothness constant is basically a constant. It does not change according to the location. But this one, when you have different, when you're at different point, the local smoothness constant is very different.
Yeah.
So that's the idea. You cannot use the global
yeah.
one. I think you have a paper about
basically this stage, right?
smoothness.
First stage you can yeah, because you can take like you know, gradient step. Like even for Newton's method, right?
Yeah,
you know,
yeah.
When the point is far from the solution, it's better to take just the gradient descent step.
Yes,
When
yes.
the point in the neighborhood, right? You can use quasi.
Yeah, exactly.
Newton method.
Exactly.
Get vertex because
Yeah.
the step size for Newton method, the step size not really just one, right?
Exactly.
I mean,
I think the idea is
so it's
very
a similar, this kind of
similar idea.
But
So
I wonder, yeah, if you could have like a high level, you know, for generic class problem.
oh, I see.
You got a kind of condition, the condition is sufficient and also necessary. That would be great.
Yeah.
It's kind of now you have a sufficient.
Sufficient condition. I'm trying to prove a lower bound, but it's difficult.
Yeah, is this optimal or not? Because
It's not optimal.
I have level work on this like federated learning or local SGD. Because you have this kind of aggregation, right?
Yes.
That can slow down the
Exactly.
convergence.
This paper has some lower bound.
1OK is optimal or?
No, it's not optimal. So this is the lower bound for this class of functions.
Yeah.
This is lower bound for this field optimization. But this is for this class of problem, but for the logistic regression or machine learning problem in general, there's no lower bound.
But even for this one, for each like this agent, whatever you call, so we have a stochastic optimization. It's not a finite sum, right?
It's stochastic optimization. I didn't add a noise part here because I didn't add noise.
Oh, okay.
But they have some noise lower bound there. Yes.
Okay, so you treat it like a finite sum problem. You
can understand it can be their lower bound can apply for finite sum, but their lower bound is really stochastic.
Yeah, but this problem if that applies stochastic, right? It's like
Yes.
SVIG. Of course, that's not a parallel It's not like this is kind of like a local SGT.
Uh,
But then you get rate, right? Rate would be better, right? Would it be?
I think this lower bound can be deterministic gradient descent, local gradient descent.
You use a stochastic, that's like SVRG.
Uh-huh.
This is right for finite sum, not to talk about expectation. Let's see.
Okay.
For each agent, right?
Yes.
Just we minimize the finite sum.
Yes.
Finite data, okay?
Okay. Mm-hmm.
No expectation.
Mm-hmm.
And then the rate would be the complexity would be like a what of 1 over epsilon square root of epsilon.
Yeah. Uh-huh.
Or what of 1 over k square.
Okay.
But then this case, if you apply this kind of federated learning, then just the what of 1 over k, right? Then you said it may not be optimal.
I don't think I'm optimal. I'm the first one to show the k is useful here, because I have the k dependency. Where is that?
I think what of 1 over k may be normal because you just noisy, right? You just can view as like inexact gradient. You take an average, right?
I take average.
Yeah, if you wanted to get if you want to improve this or reduce the inexactness, you have to do more communications. So that's a trade-off.
I see.
That's why probably it's very difficult to improve to get like a word of 1 over k square. So you have maybe word of 1 over k, maybe.
I don't think this one is tight, but I have k here. They don't have k. That's the key message.
Yeah. That's why I haven't worked on this.
Yeah. We can
just the intuitions, kind of intuition.
Yeah. Thank you for your comments. Some
There's a
Zoom
question.
question.
Yeah. Okay.
2 questions. What happens for heterogeneous weight? What's the meaning of heterogeneous weights? What does global optimality guarantee scale with number of layers? Will the guarantee beyond 2 layers? How can I adapt? Okay, I don't understand your first question. Vivek, right? I don't understand your first question, but I can understand your second question.
Yes.
Okay.
Yes, can you hear me now?
Yes.
Hi, thank you for the talk. What I meant in this 2-layer architecture that you presented, I think the weights that are in between the layers, they were all taken to be same, I think, right? The same parameters of in the second part of the talk. That's what I meant by homogeneous weights. Yeah, in this, I think you were assuming V to be the same, I think, right? For all.
V is the same. V is the first layer and A is the second layer.
Oh, I see. Okay. Then maybe I misunderstood. That's okay.
Yes.
Okay. Yeah. Then can you just answer the second? Yeah. Thank you.
Yeah. Second question is deep neural network. Okay, that's a very good question. So my analysis works for 2-layer because the 2-layer I can describe their landscape. I know there exists one superior local minima and one global minima. But for deep neural networks, I don't know. To the best of my knowledge, I don't know the landscape looks like. So I don't know if we can scale that. I think empirically, definitely yes. But if we want to prove something, we want to understand the landscape before we prove something. But empirically, both empirical statement holds for deep neural network. So I think the similar proof should go through. But I don't have concrete idea of the landscape, so I don't know the concrete proof right now. Does that answer your question?
Yeah, that gives me some idea. Yes, thank you. Yeah.
Okay. The second question, Daniel, in the first theorem, bound 1 over k r minus r0 means k is large mass. Yeah, that is right. So, okay, if you check this statement, I said for the large enough r, local GD for logistic regression have convergence rate 1 over kr, because I want to make sure r0 is not dominating compared with capital R. Yeah, I think your understanding is right. Typically, the k is constant and r is not constant. The order of r should be larger than the k, because we want to run until convergence. If your r is small, there's no way to converge, right? Okay.
Other questions? The audience here. So just to follow up the 2-stage algorithm, so what will be the implication for neural training?
Neural training, you can use large learning rate. You don't need to use.
But when do I switch?
When do you switch? When your loss is small.
Okay.
When your loss is small, yeah. When your loss is not very large, your loss is small, you can switch.
Okay,
Maybe better to identify this curvature
But-
information
but-
and
but-
smoothness.
Smoothness, yes, smoothness.
Yeah,
but no, but the thing is that this is opposite to what people are doing because practically, when lots of small, people are actually using very small learning rate, right? In
Yes.
practice.
Yes, in
What
practice.
you suggested here is the opposite, right? Initially, because you use smaller learning rate, but later it is a lot.
Oh, okay, I see.
right?
I think the gap is that this is only logistic regression, it's not neural network yet.
Yeah,
For neural network, we have different analysis. I think you should use larger one and then use small one.
yeah, okay.
Maybe the smoothness, right now I need the smoothness to be small. That's the picture proof. And the smoothness need to be small. But for the neural network, you have the first layer, so you don't know if it's small or not. Yeah, but if you are doing something like the domain adaptation, you only update the last layer. I think you can use large learning rate.
Mhm.
Fine tuning is a kind of task. You learn representation by pre-training.
Fine tuning people typically use very small learning rate.
Really?
Yes, because your data sample is too small. If you
Oh, yeah,
use
no,
large
no,
learning
no.
rate, you quickly overfit and you just forget.
Oh, I see. This one is pure optimization result. There's nothing about generalization. This is a pure optimization. Optimization is faster.
Okay.
Yes.
Okay.
Thank you.
Any last question before we close? If not, let's end the speaker again.
Thank you.